Okay, 8th grade. So our learning target today is I can write and use an equation in y equals a times b to the x to model exponential change. So we're going to be thinking about that exponential change, or where it just kind of explodes. We will not have the same slope every time. It's just going to be a quick explosion. So the difference between the two would be what we're going to talk about today is where we have tiny little growth, tiny little growth, tiny little growth, and then a great big explosion. This is my graph of y equals a times b to the x. So we've been used to a linear growth or a straight line growth. It's going to change a little bit today. So let's talk about what we used to know. So I'm going to draw a blue line here to kind of separate our thoughts. What's the difference between linear change and exponential change? Linear change is a linear line. So there's a line happening here. Here's your line. It means it's the add or subtract the same number to each step. So we have what we have in that case is the same growth. When we talk same growth, we're talking same slope. Same steepness, growing the same amount each and every time, rise over run. So in this particular case, if we start at 10 cents and we finish at 50 cents, what's the growth? So I'm going to give you a second to see if you can figure out the rule that would allow us to get through this pattern, starting at 10 cents in step 0 and going all the way down to 50 cents. Go ahead and take a look at that and see what you come up with. So you're looking to try to see the pattern between 10 cents and 50 cents from step 0 all the way down to step 5. So some options in doing that, you could find the slope. You could say y2 minus y1 over x2 minus x1. You could do some of that stuff. Or you could just look for pattern. So everybody's trying to find the pattern there. So what you should have found is that the rule is 8 cents. And if you didn't have enough time there, go ahead and pause the video now. Rule is 8 cents. So we're increasing by 8 cents every time. This is addition or subtraction. So we would add 8 cents, which is 18 cents. Add another 8 cents is 26 cents. Add another 8 cents is 34 cents. Add 8 cents again is 42 cents. And so then our pattern is that the slope is 8 cents. It's the same amount every time, gives us that linear, that straight line growth. So we end up with an equation of y equals mx plus b. We're used to doing that. Beginning amount was 10 cents. So our price at the very beginning was 10 cents. So I'm going to write that as a decimal, 10 cents. Our growth is 8 cents, so 0.08 cents. So there would be our linear equation, straight line growth, same slope, same increase as we go, starting at 10 cents. So how does that change? If we start with 10 cents, but we grow exponentially. So exponential growth is a little bit different. We're looking for multiplication and or division when it's a decay, but this is a growth. We're getting bigger, so a growth, multiply the same number to each step. We multiply by the same value. Another word for this would be the word geometric. This is a geometric growth or exponential, geometric or exponential. So I'm going to have you go ahead and look at the pattern here going from 10 all the way to 50. What would we multiply by each and every time? Go ahead and guess and check through that. The video is going to get quiet for a second here. I'm just going to be waiting for you to have a chance to guess and check it. Go. So again, we're looking for the pattern here. It's a multiply. Guess and check it. You should be trying some different things, trying to get it down to the nearest hundredth of a dollar. All right, so I'm going to jump in here. So you should have found that the rule is to multiply by 1.38 cents. You might have gotten it close. You might have figured out that it's between 1 and 2 cents. But if we work it all the way to the nearest hundredth, it comes out to 1.38. Multiplication is the rule. So if we take 10 cents and multiply it by 1.38, we end up with 13.8 cents. These are all cents. Multiply by 1.38 again gives us 19 cents. Just rounding through that. We're going to go ahead and round, make our life easier there. Multiply by 1.38 cents again gives us 26.2 cents. Multiply by 1.38 cents again gives us 36.2 cents. Multiply by 1.38 cents again gives us 50 cents. So our pattern all the way through is to multiply by 1.38 as our growth. So our equation this time would be y equals a times b to the x. A is our beginning amount, or our beginning amount is 10 cents. Our growth is 1.38 to the x power. So we have y equals 10 cents multiplied by 1.38 to the x power. All right, so we're gonna focus now just on exponential growth, where the graph just explodes. Let's go back up and kind of talk about the difference again and what the graphs look like. So a linear graph here on the left would be a graph that has the same slope, maybe starts here at this B, same slope every time. That's linear. Exponential growth grows very slowly with a quick increase. It just kind of explodes and increases. So that's the difference between our linear and our exponential growth. We're going to look at just exponential today. So let's talk about this starting amount in my bank account, $2,000. That would be my A. My annual interest that I'm going to earn is 5%. So let's think about what that really means. Our value is that we get all of the money we put in our bank back plus 5%. So we really get 100% back plus 5% increase. So that really becomes kind of 105%. We're going to talk about how to work through that as we go. So our beginning amount at the beginning of the year is $2,000. That's my A. So my equation y equals a times b to the x. That's my A value, 2,000. My growth is 5%. But keep in mind that we do get all 100% of my money back plus 5%. So that's 105% in decimal form is 1.05. So my growth then would be beginning amount is 2,000. And I get 100% plus 5% back. I get all my money back that I put in, $2,000 plus a 5% interest growth. So I'm going to go ahead and multiply that in my calculator. Everybody grab that calculator. It's 2,000 multiplied by 1.05. Go ahead and type that in. 2,000 multiplied by 1.05. And the ending amount then is $2,100. We have $2,100. So now when I go into the beginning of year 2, I get, this is my amount that I'm going to start with, which changes it to a compound situation. So now I'm starting with $2,100. My growth is 5%, but remember we get all 100% back. So I get 2,000 at the beginning. I get 1.05 for the first year and 1.05 for the second year. First year and second year. So I get all my money back plus a 5% interest growth in each of those years. So go ahead and multiply that in your calculator. 2,000 multiplied by 1.05 multiplied by 1.05. So you end up with $2,205 at the end of year 2. So you can see that I've already increased my value by $205 in just interest amount there. So when I go into year 3, I have $2,205 at the beginning. My initial, if we use this equation now, my initial amount that I started with was 2,000. My interest growth is 1.05. It's 100% of the money comes back plus 5% is 105%. In decimal form is 1.05. And for 3 years, I need 3 of those. So instead of writing it out every time, 1.05 times 1.05 times 1.05, I'm just going to say that that's to the third power, 3 of them. Go ahead and type that in, 2,000 multiplied by 1.05 to the third power. Gives us an output of $2,315.25. Go ahead and double check that in your calculator. Make sure that that's the value you have. All right. Plug in through here. Why don't you go ahead and keep following that pattern for years 4 and 5. The video is going to get quiet here for a second. Go ahead and try to finish table through year 4, year 5. Go. Everybody should be working on year 4, year 5. So as we start to solve here, we're going to use the ending amount at the end of year 3 as our budget for the beginning of year 4. So we're going to go ahead and just run that value right on over as our beginning amount. So we end here, which is our beginning amount in year 4. We are going to be getting an increase of 5% for 4 years straight. So that's 1.05 4 times 1.05 times 1.05 times 1.05 times 1.05. That's too much to say. To the 4th power. So we're going to do that 4 years in a row. Our output then is $2,431.01. If that's too much for you to understand what I'm saying there, I'm going to go ahead and highlight in blue so you can see what I'm talking about. Now that blue highlighted number is going to be our beginning amount as we go into year 5. If this is way too fast, you need to pause that video. If you have a sub today, you should be very politely, respectfully asking the sub to pause the video. As we go into year 5 then, your beginning amount is $2,431.01. And we are going to increase for 5 years now. So we have that beginning amount of $2,000. Our growth is 5%. We're going to do that for 5 years. So 2,000 times 1.05 to the 5th power. Our final output at the end of year 5 then is $2,552.56. Now you can see that if we started at $2,000, we got a huge growth after 5 years in that interest, which is a pretty sweet deal if it's money that is basically free money. So let's talk about some other scenarios then. So the problem that we have right now is we're depending on the previous value to figure out the new values. And you don't necessarily want to do that. You don't want to be dependent on the previous value. So what do you do if you wanted to know something about year 20? Nobody wants to make a table from year 1 to year 19. So following the pattern that's happened here, we wouldn't need to necessarily know the amount that we had at the beginning of the year. We would be able to use this formula of the amount at the very beginning we need to know for sure, our A value of $2,000, what we put in at the beginning of a time. Then we would know our increase is 1.05. It's 100% of our money back plus 5%. All we need to do then is to the power of 20 for 20 years. So we would type that in, 2,000 multiplied by 1.05 to the 20th power, and we end up with an output of $5,306.60. So we've doubled our money and more in 20 years. Super good investment if you're able to find something as good as 5% interest. Banks are not running 5% interest at this time in our lives. So let's talk about a general formula, general scenario. At year X, we don't necessarily need to know the beginning amount at the year. What we would need to know the beginning amount in time, our A value. Our growth is 1.05, 100% plus 5% bonus money to the X power. We wouldn't have an output here because we would need to know the number of years, but that's the general formula. All right, so talking about the formula we've been working through. All of these have an important piece of this puzzle. This is called exponential growth, where we explode in our growth. So the X or the Y is the amount that we have over time. How much do we have in the account after a certain amount of time? A is our starting amount, $2,000 in this particular case. X is our time. In this particular case, that changed. Some things that we thought about in this process is that the growth is our B. You're either going to, when it's a growth, it's going to be 1 plus the rate. So in this case, it was 1.05, 105%. If it's a decay, we're losing money, we're eating half the candy bar, we're spending our bank account, then we would be subtracting 1 minus the rate, all in percent decimal form. Okay, so in this next example, we're going to talk about whether it's a growth or a decay, and it's based on the B value. So if the B value is greater than 1, we're growing. If the B value is a fraction less than 1, we are decaying. The starting amount is not important. I'm not worried about the 10, just the growth of 3 there. This is going to be a growth because we're really 3 timesing. That means that we're tripling it. Growth. Looking at our B value here, again, the 8 doesn't matter. It's just the B value. That's a fraction less than 1. 2/3 is less than 1. That's going to be a decay. We're going to decrease. So that graph is going to look something like this. We start here. We're growing and approaching 0. Looking at this one here, again, make sure you're not looking at the 4 out front. That's the starting amount. This is a fractional growth less than 1, 3/8, which is a decay. Same graph. Starts up here, decays. Next problem is also a fraction, but that's the fraction 4/3. It's an improper fraction. That's a fraction that's greater than 1, so that's going to be a growth. So it starts up at 1, like they all do, and grows, explodes. So kind of the summary of what we talked about. How do you know if it's a growth or a decay? It's all about the b value. It's all about the base, the b value. If the b value is greater than 1, we grow. So the picture of that graph would look something like this. We start at 1 and we explode. If the value is a fraction less than 1, so it's some fraction between 0 and b, then it's a decay. So we still start at 0, 1, but now we're going to approach 0 all the way to infinity, getting super, super tiny. So that's how we know if it's a growth or if it's a decay. All right, moving to the top of the next page then. So we're on the top of page 17. So what kind of change is happening? So we're going to go ahead and work through this process. You deposit $500 into an account that earns 9% annual interest. How much will you have after 11 years? So we're going to use y equals a times b to the x. So we have y equals the beginning amount. We put $500 in at the beginning. And 9% earned. So we really get 100% back plus 9% is 109%. You get all your money back plus a 9% bonus. In decimal form, that's 1.09. So my b is a 1.09 to the x power, and the x is the years to the 11th power. So go ahead and take a look at that. 500 was the beginning amount. My growth is 9%, which is really 1.09% to the 11th power. Go ahead and type that in your calculator. 500 multiplied by 1.09 to the 11th power. I end up with $1,290.21. That's my finishing amount after year 11. All right, hang in there, guys. Here we go. So next one. Each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. That's sounding like an A value to me, my beginning value. During each round, half of the players are eliminated. This is sounding like a decay. Sounds like a fraction. How many players remain after 5 rounds? So y equals 128 is our beginning amount. We have 1/2. We're going to 1/2 the players. Because this is a fraction, we have a decay. We're going to do that for 5 rounds. So our time frame is 5 rounds, not years, rounds. So in our calculator, we're going to put 128 multiplied by 1/2 of the people we lose each round for 5 rounds, 1/2 to the 5th power. Our value then is we're down to 4 players after 5 rounds. We started with 128. If we keep cutting in half for 5 rounds, we're left with the final 4, as we would call it, 4 players left. All right, guys, hang in there. A couple left. A baseball card worth $150 is projected to increase in value by 6% a year. What is the value of the card after 7 years? So this is sounding like a growth, increasing in value. So we would say, what is our beginning amount? $150. Our year is 7. Now figuring out the growth, 6%. We get 100% of the money back. We get all the 150 back plus the 6% growth. So that's really 106%. In decimal form, that is 1.06. So my b value is 1.06. We have 150 multiplied by 1.06 to the 7th power. Typing that in my calculator then, my output is $225.54. That's what the baseball card is worth after year 7. If I'm going too fast, go ahead and pause that video. Next example, we have a new car that we're buying for $24,000. That's a pretty typical price for a new car. The value of the car decreases by 15% each year. So that's sounding like a decrease. What is the value of the car after 3 years? So we have y equals, our beginning amount is $24,000. Our growth. So we're growing only by 85%. So let's talk about how that works. So my little brain box down here. It's 100%. Take away the decrease is but 15%, leaves me with an 85% increase only. So we want to know what is our value. 85% in decimal form is 0.85. And we're keeping track of that for 3 years because we're depreciating or losing value. And so it's really 85% each year because we're losing 15% each time for 3 years. So as I typed that in my calculator, 24,000 multiplied by 0.85 to the third power gives me $14,739 after 3 years. So that car already lost about $10,000 in value. That is the reality of real life there, unfortunately. All right, group, hang in there. Last problem of the day before our summary. So here's our try this. We have this y equals a times b to the x. We have a times b to the x equals y. I just flipped some things around using the commutative property there. How much money was originally deposited in the account? Go ahead and look at the account. We're wanting to know what was the original amount of the deposit. You should have said $1,500 was the original amount in the deposit. $1,500. How many years was the money in the account? You should have said 7 years. How much money is the account after this time? There's my output, $2,923.08. What is the growth factor? The growth factor is my B value, 1.1. And because it's 1.1, it really means we'll put a placeholder here, 100% plus 10%. That's really what we're saying. So the interest rate then is 10% interest. That 0.1 really represents 10% because you get all 100% back plus 10%. Finally, we're done. So our summary for today is, this is our equation. Go ahead and copy that down. Y equals a times b to the x. Get all those notes in. Let's talk about what a growth looks like, what a decay looks like. Growth is if the b value is greater than 1. The decay is if the b value is between 0 and 1. Go ahead and copy those notes in. All right, guys, so your homework for this evening is to get all the way through page 20 on exponential growth, exponential decay. Again, through all the way through page 20. Have a fabulous night, 8th grade.